For online learning setting, we can provide interesting theoretical guarantee with convex objective function. This is called online convex optimization. So what is online convex optimization? So we usually assume there is an hypothesis class. So let's say H is the hypothesis class and G is input domain. Then Rho's function L is function of hypothesis and input, which will give us a real value number, Rho's function value. And assume that H is convex, so the hypothesis class shape is convex set. And loss function is also convex function for all z. Then at each time, the learner should select a hypothesis vector WT from the hypothesis class and get the loss WT and ZT for the WT and ZT. And usually we also assume that we can reveal what is ZT exactly. And also sometimes we assume we can compute the gradient of Rho's with respect to the W value for given Z. Okay, so this gradient is with respect to W. Right. So with this information, the loss value and ZT or the gradient value, we want to update the hypothesis WT so that the cumulative regret value is minimized. So what is regret? The regret is, as before, the sum of rows by our algorithm, so the sequence of our selection WT, minus the sum of rows value using one fixed strategy, fixed hypothesis, W star. And we can control W star so that the regret is maximized when we fix the strategy or algorithm. In other words, we can find W star that maximize this term, the second term, that minimize the second term, so that maximize this regret function. Okay. So the goal of learner or goal of algorithm designer must be minimize the regret. Okay, we want to find the sequence of WT so that the regret is minimized with very limited information, like only using gradient and loss value. So for the online convex optimization problem, we can design a hand-aside algorithm called follow the reader. So basically, this algorithm is very simple. So at each time we test WT and observe the loss WT with GT value. Okay, so let's assume we know exact loss function shape for given ZT is from G1 to GT at time t. Okay. Then for the next time we have to choose WT plus 1, and how can we decide WT plus 1 using all the information WT and loss value with respect to ZT from t equal to 1 to current time slot. How can define WT plus 1? We just use hand-aside rule, just try to minimize the loss value up until now. Okay, just consider sum of, for the WT, just consider rows sum from I1 to t minus 1. And then just try to find the W, hypothesis W, then minimize this rows function, sum of rows values. Okay, so this is called follow the reader rule, and this simple rule can basically give us very nice regret bound. Okay, so to show the regret bound, let's first start with this very useful lemma that looks like very intuitive and looks like very trivial, but needs some proof for vigorous statement. Okay, so what is the lemma? So when we follow the reader rule, when we use follow the reader rule, and if we can use the follow the reader rule before learn the algorithm, like if we can access to loss zt, loss with respect to zt before choose wt, then basically we can play wt plus 1 at time t. Of course, this is impossible rule because we cannot observe zt before playing wt, before we play the function at time t. So this is not possible at all, but let's assume some God help us. So we know zt play before playing wt, so we can play wt plus 1 at time t. Then this sum of loss value might be very nice, even much better than any fixed algorithm. So this lemma is about this statement. So when we play wt plus 1 at time t, the cumulative loss from time t1 to capital T is less than or equal to the sum of loss for any fixed hypothesis W star. Okay. How can we show this? So just for notational simplicity, let's use ft as loss at time t, loss with gt. And we use the mathematical induction to show this lemma. So when t equal to 1, when capital T equal to 1, the lemma is true just from the definition. And assume that the lemma holds for capital T minus 1. And of course, capital T is greater than 2. Then for all W star, we have this from the assumption. Okay? Since we assume that the lemma is true for capital T minus 1, we have this. And to make the statement at capital T, let's add ft wt plus 1 to both sides, here and here. Then the summation goes up to t minus 1 to capital T, because we add ft wt plus 1, right? So we can write this. For the right hand side, we just add ft wt plus 1 to this. Okay, we have this. Right, so when we set w star to wt plus 1, this is just summation from 1 to t ft. So this is just equal to t1 to capital T ft wt plus 1. And from the definition of wt plus 1, w capital T plus 1, this is basically the optimal hypothesis that minimizes the cumulative loss. So from the definition, this is equal to mean of w in the hypothesis that minimizes the cumulative loss function wt. So the lemma holds for capital T as well. So from the mathematical induction, when t is 1, this is true. t is 2, true, because t equal to 1 is true from the definition. Since t equal to 2 is true, t equal to 3 also true, and so on. The mathematical induction tells us for all capital T, we have this. It looks like trivial, but rigorously it also holds with the following proof. Okay. Okay, then regret of follow the reader rule is analyzed by this inequality. From the lemma, we can simply replace the ftw star by ftwt plus 1 because we know that sum of ftwt plus 1 is less than the sum of ftwt. Okay, so the regret can be upperbounded by this. So when we consider this lemma already very useful when you consider ft as kind of mean squared error or L2 loss with respect to some arbitrarily selected zt vector. Then Wt is just empirical average of z1 to zt minus 1 from the definition, and thus ftwt minus ftwt plus 1 can be written like this and upper bounded by 1 over t wt minus zt normed square. Here we use the definition of wt plus 1 and wt. So when the zt, the norm of zt always bounded by some capital L, so when we have some bounded domain of zt, then from the triangle inequality, we know that the norm of wt minus gt is bounded by 2L, right? So from this lemma, we can say that regret follow the reader rule is upper bounded by 4L square times log t plus 1. So 4L square comes from this, since ftwt minus ftwt plus 1 is bounded by 1 over t wt minus gt normed square, and the normed square is upper bounded by 4L square. We have 4L square here, and the sum of 1 over t is bounded by log t plus 1. That's it. Okay, so using this very simple lemma, we can easily analyze the regret of follow the reader rule. Okay, just pick the best one, only use the data collected. Still, it is very nice. But follow the reader rule is not always good algorithm. Okay, this is good for kind of this mean squared error or L2 loss form, but there is some counterexamples that explain FTL can be failed, totally screwed up. For instance, when the hypothesis class is 1D dimension interval from -1 to 1, and consider the sequence of linear functions instead of the degree 2 square function, such that ftw equal to gtw, where gt is follow this rule. At time t equal to 1, it is equal to minus 0.5. When t is even, so t is equal to 2, 4, 6, 8, and so on, gt is equal to 1. And when t is odd and strictly greater than 1, and gt minus 1, which means ftw function, it starts from minus 1 over 2w, then it becomes w minus w, w minus w, w, and so on. So to optimize this function, some of this ft function, we have to choose +1 here and -1 here, +1 here, -1 here, +1 here, -1 here. Okay, so this may be W2, this should be W3, this should be W4, and so on. But unfortunately, +1 is +1 maximize the second loss function, -1 maximize the third loss function, +1 maximize fourth loss function, and so on. So follow the reader rule, just maximize the loss function. Okay, so which means the regret grows linearly very rapidly as t grows to infinity. Okay, more precisely, when we fix our hypothesis to 0, when we set W star equal to 0, we basically have 0 loss value all the time, so the cumulative loss is equal to 0. But when we follow the reader rule, we always maximize the loss value adaptively, very bad, and the cumulative loss grows to just t. So the value we obtain is, the regret value we obtain is capital T. Very bad. Okay. So maybe we need something else that universally good. Okay. So the main goal of this chapter is, let's design a universal algorithm that works well for many classes of loss function. Follow the reader rule is very simple and very intuitive idea, but the problem is, although this FTL rule is very nice for the L2 loss, mean squared error regression problem, but this rule also has many counterexamples. The regret grows linearly.